The quantum revolution, Bell's theorem, and the end of local hidden variables. So at this point in the chapter, we're now in through the EPR paradox and what that means. And Bell's theorem comes in and disrupts all of that. So in this problem, we have an example of this theorem. So one example of a local deterministic, quote, hidden variable theory is classical mechanics. Who would have thought? Suppose we carried out the Bell experiment with a classical object, baseballs say, in place of the electron and proton. They are launched by a kind of double pitching machine in opposite directions, with equal and opposite spins, angular momenta. So SA and SB, which is equal to negative SA. Now, these are classical objects. Their angular momenta can point in any direction, and this direction is set, let's say randomly, at the moment of launch. The detectors placed 10 meters or so on either side of the launch point measure the spin vectors of their respective baseballs. However, in order to match the conditions for Bell's theorem, they only record the sign of the component of S along the direction A and B, where A is equal to the sign of A dot SA and capital B is equal to the sign of B dot SB. Thus, each detector records either +1 or -1 in any given trial. In this example, the hidden variable is actually the orientation SA specified, say, by the polar and azimuthal angles theta and phi. So lambda is a function of theta and phi. So for this problem, this is the picture given to us, the diagram. And part A tells us to choose axes as in the figure with A and B in the xy plane and A along the x-axis. And then we want to verify that capital A with the vector A hidden variable lambda, same thing with B, is equal to negative sine cosine phi times cosine phi minus eta, where eta is the angle between A and B taken a run from negative pi to positive pi, as we see here. Okay, and then in part B, assuming that the baseballs are launched in such a way that SA is equally likely to point in any direction, compute P of AB and given the answer. Then in C, we're tasked with sketch the graph of PAB from eta equal negative pi to positive pi, and on the same graph, the quantum formula from 12.4 with theta going to eta. For what values of eta does this hidden variable theory agree with quantum mechanics results? And then D, classify or verify your result satisfies Bell's inequality from equation 1212. Hint, the vectors A, B, and C define 3 points on the surface of a unit sphere. The inequality can be expressed in terms of the distances between those points. Okay, so this is a pretty hefty problem, so let's take it down part by part. Why we care is because of the concept of local hidden variables. And this is the concept where in the EPR paper, Einstein had such a, big bombastic opinion on, because if things are entangled, so to speak, then the information of one state gets to the other state, or the measurement of one state automatically tells you the understanding of the other state. And this just didn't make sense for relativity and what Einstein had in his mind from the classical version in the classical era. So that just didn't make sense. So his postulate was that quantum mechanics is incomplete and thus there's some hidden variable there. Okay, and that's was shaking up the world in the 1930s. Okay, but with Bell's inequality, we prove that this gets eradicated, or at least subjugated to another discussion. So the challenge still remains, though, what does this mean for the nature of reality? Is this concept of that these systems are intricately linked and it's just an intrinsic part of nature, then we have to describe them like this? Like what does the actual meaning of this all get to? And I think that's the hardest part about quantum mechanics is the interpretation that we have with it. I know every time I try to dive in deeper on the meaning, my head just explodes. So I'm assuming I'm not the only one. That being said, there is a lot in this problem, and I think it's better organized in the PDF. So if you want that, feel free to use the Patreon link below or just comment and I'll send you the link directly to this post and we'll be good to go. Now, before we begin, you should know that my goal is to break down these complex physics concepts using the exercises from these top books. If that sounds like something you'd enjoy, hit the subscribe button and join us in exploring the universe. Now, let's get on to part 1. Okay, so to start this solution, what we need to first do is to begin, we'll construct vectors a and b in component form based on the figure that was given to us. So since vector A lies on the x-axis, we know that that's only whatever magnitude in the I direction because that's the x direction. Since we're unitizing this thing, we can just put 1, 0, 0 as the vector. And that, again, the local variables are angular, or the quote local hidden variables are angular, so that's what we're actually trying to get to, not the magnitude of this. Secondly, B is in the xy plane, so we know that based on the distance between these two, eta, we're good to go. We just have cosine referencing the x-axis, since that's where A is, and sine referencing the y-axis due to where A is. So, again, normalizing it to where the coefficients are 1, we're good. We can divide that out. That being said, we need to construct the S vector in component form as well. Now, that was in the 3D space, okay? So here, we don't know what's going on with S outside of the component form, so let's just break it down. The magnitude, cosine phi, sine theta, magnitude, sine phi, sine theta, and then magnitude, cosine theta. Okay, this was the polar angle and then the azimuthal angle phi. Okay, so this is looking familiar. Let's just go ahead and put it into the angle bracket notation to keep it tidy since we know we're in X, Y, and Z. That being said, we can factor out all the S's from every component. And then we know that the spin B is negative SB, so we're fine. We get the same thing. So now the goal all along was to prove that the product of these hidden variable quantities, which are both the signs of the hidden variables on their vector components, is negative sine, cosine phi, and then cosine phi minus eta. Okay, so in order to address this for these products, we need the dot product of A and SB and B and SB from the A and B local variable definitions. So let's get to chugging that out. Okay, so now the dot product here of A dot S, well, given that we're only in one direction for A, that just means we need the first component here, so that one's pretty easy. Now for B, since we kind of know what we're looking for, the only thing that survives since B is in the XY plane are the XY coordinates added together, negative out front due to definition, and then SA magnitude. Both of these have a sine theta in them, so we can just factor that out. Then from there, we see that the cosine eta, cosine phi plus sine eta, sine phi, that's a sum and difference identity. So we can write that as the difference of cosine phi minus eta. And that's pretty easy. We actually simplifies it down quite a bit right now. Later, when we get to the probability, that's going to come back and we're going to have to be very careful on our cases. That being said, from these dot products, we know that the polar angle runs from 0 to pi. So the sign for the polar angle is always positive. Remember that 0 to pi is on the top half of the unit circle, and since the top half represents positive y values, we're all positive. So when we're looking at the sine function itself, we see that this doesn't do anything. So we're good, positive, positive, everything so far, and all we have left is the sine of cosine phi. We don't care about the magnitude, so we just want the sine of it. Then in B, we have a negative sign already inside. Since sine is positive, we know that that positive negative makes a negative, so you can put that negative outside, good to go. That being said, you still need to find out what the sign of this cosine phi minus eta is. Okay, so when multiplying these two things together, you get the sine of cosine and the sine of cosine with the difference here all together. So we did indeed prove the product of AB for the local hidden variables. That being said, what do you think about this so far? Drop a comment with your thoughts below and let's have a discussion because this thing is kind of crazy and it's about to get worse. Okay, so for stop number 2 then, for SA to have equal probability in all directions, we have to consider the coordinates in spherical coordinates, which is given to us on a unit sphere. And this is important because this is where the probability is proportional to the surface area of the sphere. And since we know that probability has to be conserved and things like that, they need to add up to 1. So normalization is essential to ensure that this probability sums to 1. And to achieve this, we use the weighted average formula that accounts for the necessary normalization. This approach guarantees the uniform directional probability for SA, so we're good. That being said, the weighted average here, what we see, product over the angles, and then just divide it by whatever the results of the angles were, so now we're good. As you see, plugging in everything leads us to this. As you see, angular integrals, we've done them 1,000 times already, so let's get to it. Negative sign pops out. Fubini's theorem allows us to split these into separate arguments, color code it. The green and green yield the same value, so they cancel. And now you see that we're stuck with this nasty integral here. So let's set up a game plan for identifying what this yields. Okay. So now that we have this quote normalization outside with the negative sign from the arguments, we're good to go. And now what we have to do is investigate what happens on the inside of the sine function that's in the integrand. Okay. So we know that cosine phi is positive for all values on the unit circle to the right of the y-axis. So positive unless we're between pi over 2 and 3 pi over 2, so the left side where it's all negative. And so here, when we plug this difference argument in, we see we have the same bounds, but then we have to add eta to both sides. So in order to address where we're positive, where we're negative, let's first split eta up into 2 since we know it runs from negative pi to pi. Let's split it up from 0 to pi and then investigate what happens on that stretch. Okay, and to do that, we split eta up from 0 to pi to 0 to pi over 2 due to the inflection points that we see with the result of phi. Okay, so starting with this as our first augment, we see that going from 0 to eta is the first segment, but then eta can go to pi over 2, okay? So once we start here, now we're looking at what happens to phi. Okay, so if I add eta to pi over 2, then I go to pi, then I go to pi plus eta, then I go to 3 pi over 2, then I go to 3 pi over 2 plus eta, finally to 2 pi. So if we kind of mark this out right, we see that our turning points classically are pi over 2, pi, 3 pi over 2, and then 2 pi. So now we just have the weirdness of adding eta in between every segment, right? So eta, 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 and one more. All right. So now we can see that we're going to have different combinations of plus or minus here. So if we look at the plus signs here for segment 1, we know that both are going to be positive, where this is the first term, this is the second term. So since we have cosine of phi, where phi is between 0 and eta, which again is less than pi over 2, then we know that that's positive. Same thing here for cosine of phi minus eta, that's going to have to be positive. So once you go through and see what happens with the product inside here and just make plus plus, plus minus, whatever combinations they are for their arguments, then we can see that the total from their products are going to be positive, positive, negative, positive, 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 negative, positive. Cool, no big deal, just very time consuming and chunky to set these up. So once you get this, then we can plug these results back into the integral, since we know we could split up the integral by segmenting the bounds on it. So let's see what that looks like. So the probability here, after we segment the bounds into these partitions, we see that again, the sine function only wants the signs. We don't care about the magnitude. As a result, we get the plus, plus, minus, plus, 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 minus, plus. So now we see that we can just evaluate them at the boundaries since it's an easy integral. So that's eta minus 0 all the way down to 2 pi minus 3 pi over 2 minus eta. And you see inside a lot of these parentheses, we get cancellations out, so that's easy. Then once we distribute negative signs or just see what happens after those, we get cancel, 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 and then we're left with 4 duplicates of this 𝞹/2 minus eta, upon which that simplifies really quick. So 4 and 2 reduce to 2. Now we have to distribute this, so that's where we get a cancel, cancel, minus sign, cancel, so we get 2 eta over pi minus 1. All right, cool. Now, this whole thing really works because cosines are even functions, and we'll see how that's summarized here shortly. But because of their evenness, we know that whatever happens from 0 to pi will also happen from 0 to negative pi. So that's what we're kind of archetyping this on, and why we're splitting up the eta segments from 0 to pi/2, so we could see what happens on this difference in the cosine. So let's go do the other half of this 0 to pi split up and see what we get. So since our first split was from 0 to pi/2 for eta, this one's going to have to be from pi/2 to pi. Now upon which we see that we're again starting at 0, working all our way up to 2 pi. And you see that we have 8 segments once again. Once again, our cornerstones here. Let me get my colors. We have pi/2, pi, 3 pi/2, and 2 pi. And then we have our eta being a minus now in between everything. So once we do that, then we're good to go. And now I can plug in the integral, set it up here. A lot more minus signs now than before. I think we only had 2 minus signs last time. Now we have 6 of them. So they kind of flip-flop as you'd expect. So evaluating the integrals that were segmented again leads to a very similar result, 2 eta over pi minus 1. So again, since these cosines are even functions of the integral is also an even function of eta. So consequently, we can generalize this result to the magnitude of eta equals constant, where the absolute value notation indicates the relationship holds true for both positive and negative values of eta. So that's why we only had to split up the partition from 0 to pi instead of negative pi to 0 as well, because then they're just the same thing. Okay, and this simplification allows for a more concise and universally applicable expression of the integral behavior as the probability of AB equals 2 absolute value pi minus 1 for eta between these two values. And again, traditionally we would just add these together, but then we get 2, and then we'd have to divide and all this other stuff. What this is highlighting is that this probability is going to be consistent amongst to the right and to the left, and that's really cool. So if you're finding this helpful, don't forget to hit the thumbs up. It helps more curious minds like you discover this content. Now that we're done with this mega mess, let's go ahead and simplify or finish off this problem by graphing and seeing how it holds up with Bell's inequality. Okay, so this leads us straight to stop 3. From equation 12.4, the quantum prediction here is that the probability is AB is just the negative dot product. Okay, so take the negative dot product here. We see that we just get negative cosine eta. Now this looks really similar to the negative Taylor series expansion of cosine for the probability we got in part B. So let's see how close exactly. So graphing this, which again is available in the PDF and the Desmos link that I made this in, here we see that the green is the cosine, which is the quantum prediction, whereas the blue absolute value is the classical prediction. Okay, and you see that they meet up at random points. So pi/2, 0, pi/2, pi, positive or negative. That's the evenness coming through again. So this is pretty wild, right? Now, again, depending on how you wish to normalize this and shift it, I've seen graphs that are inverted of this as well. Okay, so be aware of that moving forward. What we also know is that because of this, with Bell's modification then, the EPR paradox proves something far more radical than its authors imagined. Now, if EPR, the Einstein-Podolsky-Rosen, if they're right, then not only is quantum mechanics incomplete because of these hidden variables, it's downright wrong. Okay, so that's kind of crazy. But with everything else that suggests quantum mechanics is right, this means that on the other hand, if quantum mechanics is right, the no hidden variable theory is going to rescue us from the non-locality Einstein considered to be preposterous. So this spooky action at a distance has to be something intrinsically linked to quantum mechanics, which is brain hurt for real, and there's really no way around it. So that's pretty interesting. That being said, the graph is now done. We saw where they were equal, and now we can move on to our final stop, which is evaluating Bell's inequality. And this is the famous inequality that we saw from the aspect experiment, or Aspen, one of the two, I can't remember right now. But what it says is that for the probability of AB and then minus the probability from A to C, that difference here has to be less than 1 plus the probability of B to C. So now that we know what the general form is for this classical expression with the absolute value over 2 absolute value over pi plus 1 or minus 1, we can just go ahead and plug this in for the paths A to B, A to C, and B to C. And that's what we see here, A to B, A to C, B to C. And as we see, plugging them in, -1, +1 from this negative sign here, cancel, cancel. This one and this -1 here, cancel, cancel. So we're good. Now we see that on the inside, we have 2 pi factors on the inside of the absolute value. Factor them out, get them outside. 2 pi over here. We see the 2 pi's cancel. Beautiful. And now we see that this looks like just the distance formula, where you have some distance here and the absolute value has to be less than some other distance. Okay. And I'm going to highlight specifically here AB, AC, and BC because eventually this will make sense when we chain them together. Now we need to note that again, the 𝚹s are all from -pi to pi. That's what was given to us. So now that we have that, we can go ahead and stipulate why this inequality makes sense. Okay, so the real thing that we need to do here is to address the absolute value on the left-hand side. To do this, we need to consider two distinct cases. One where the A to AB is greater than AC, and one where it's less than AC. Okay, two cases right here. So for case one where we're greater than AC, then we know that the value on the inside of this is going to turn out positive, so we can drop the absolute value and we're good. Upon dropping it, we see that we have AB minus AC equals or is less than or equal to BC. So add that over. And now you see you get the indices AB, AC, and BC. Okay, but what we know we can do here is that because of this, right here, this quote-unquote metric, we can switch the indices BC to CB. And this can be done because the dot product is commutative. BC equals CB, so we're good. So now we're running from AB, and then over here we have AC to CB. So that tells us that we have going a direct path versus two segmented paths. And we'll see what that looks like in just a second. Similarly, if AB is less than AC, then the magnitude here, in order to get rid of it, the absolute value signs, we're going to have to impose a negative sign on it. Because whatever's inside here is going to be negative, so we have to impose a negative to make sure we have a positive value. Now doing that, we distribute that in. We see the negative on the AB now and a positive on the AC. So go ahead and put that in rearrangement. So AC minus AB. Now when we compare via the inequality from Bell's theorem, we get A to AC minus AB is less than or equal to BC. Add this blue term over. Then you see you have a direct path A to C is less than A to B then from B to C. So in both cases, the equations state that one angle is smaller than the sum of the other two. And this is logically sound. Let's actually take a look at why, how or why this is. So here we have a unit sphere, okay? And if the vectors A, B, and C define points on a unit sphere, then we know that the angles between the vectors are proportional to the lengths of the great arcs connecting these points. In particular, the inequality express that, let me get my pen out. Okay, so the direct path here, in our first example, we saw that it was AB, right? So our direct path from A to B, okay, that's much less than going from A to C and then from C to B, okay? That makes sense. Direct path from A to B is shorter than A to C than C to B. Okay, here's the geometry as to why. Now for the second inequality, or the second case for the inequality, the direct path from A to C is less than the direct from the alternating path from A to B, then from B to C. Okay, and that's the argument there. So what this reflects is the geometric principle that a straight line is the shortest distance between 2 points unless the third point happens to lie directly on the path. And expanding that to spherical geometry, the same thing is going to hold here as we see via the angles and the great arcs. So that's pretty darn cool. So with that, we have successfully shown that Bell's theorem and inequality hold for even this classical example. And this changed everything because what it did was eliminate the concept of local variables from this quantum system idea. And now we have to look at what about global or global hidden variables. And that's going to be a conversation for a different day, but the papers on this stuff are very crazy. So definitely keep your mind open for it because this theorem flipped and revolutionized quantum mechanics because it showed that entanglement has to be a part of these systems as of this day. So lots more to be said about this, and we'll get into the paper reviews after we're done with this chapter, so be on the lookout for that. Whew, okay, so I was not sure what to expect from that video, but I'm glad I'm glad we were able to make it because that was a whole lot to put into one space from one problem. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions will make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in joining the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.